Okay, so what I'm going to do is I'm going to share my screen in just a sec, and we'll sort of look at like what the current status of the simulation is. And then from there, we can look at what it takes to refactor DC. We're probably not going to get all the way through it, but at least chatting through a few of the steps I think will be useful. So let me just pull up SimPEG as well. Okay. Sorry, my screen is a little chaotic at the moment. So we're getting it organized. All right, here we go. Cool. So let's just zoom into this notebook real quick. So
Lindsay, can you make it even bigger?
Yeah, for sure.
Yeah, so I have low resolution on my screen.
Yeah, no problem. Sometimes the Hangout.
Okay, it's better.
Okay, so the goal here being that instead of having the problem and the survey, we now replace that with the simulation class. And so the simulation, what it has is it's going to have a few things like deepred. In this case, because it's a linear problem, it has a G, a get J, JBack, all of the things that we used to have in the problem class are now in the simulation. And one of the important things in this refactoring is the fact that we can actually serialize. So if I look at now, we've created this simulation. It has a mesh and it's got a model map because yeah, so we're using an identity map in this case. And so, so here, what that means when we serialize it is we can basically write all of the parameters that you need to reconstruct the simulation class in a simple JSON or a dictionary. So here you can see that, for example, when we serialize the exponential sinusoid simulation, the simulation that I set up, it serializes the mesh. And since the mesh is actually also a serializable thing, it goes in and writes out those properties so that the mesh can be reconstructed. Then here we have the model map. This is one piece that we still need to go in and make sure it can be serialized. So that's not done yet. But then we've also got things like the number of kernels and then a couple tuning parameters on what that simulation looks like. So here, if we go to the simulation, can you see that okay?
Mm-hmm.
Perfect. So here, if we look at, I've got the exponential sinusoid simulation, you can see things like the number of kernels. So here that's serializing, right? And then the P and the Q are just describing like how we actually construct the kernels. And so those are then parameters that the user can set. Okay. Does everybody sort of follow that? Any questions?
Yeah, you think in the long run, you think we can do the drawing the mesh in the compact form, you know, with the number of cells times the cell dimensions? Because I can foresee that when you're gonna get like 2D or 3D, like storing it with integers or floats for each cell is gonna get ugly, right?
Yeah, that's a good point, Dom. And yes, we can absolutely do that. So that is just a function then of how we choose to serialize it. So we can customize that piece. And what's kind of nice is like this should sort of be forward compatible in a sense of like what we currently do. And if we actually decide to write things to a more compact form, there shouldn't be any conflict. That should all be under the hood.
Okay, so serialized, we have access to the knobs for how it's stored, or
yeah. So one example of that I can show you. Rowan gave me a snippet here because to serialize the solver. So here, if you look at the solver, which we probably haven't set yet. Yeah, so we haven't set that. But the solver actually is a class, and so that wasn't like a built-in property in the properties library. So at first we didn't know how to serialize it, but the only thing that you actually need is the name of the solver and the class. So here, let's set that up and see what that looks like. So here I'm going to import Paradiso. Okay, and then here when we set the solver, okay, and then if we serialize that, sorry, then here what we've done is we've said the class is Paradiso. It's coming from the PyMat solver module, and it's this version. And so here, if we actually look at the code, that was all specified by this to.json. And so we actually have access to how any of the properties serializes. Does that make sense, Dom?
Yeah, so they all, like, if we want to define one, we just need a to.json and a from.json.
Yeah, absolutely.
Right, perfect.
Yeah, so that's kind of cool. Yeah, okay, and then what else has changed? Okay, let's then take a look at perhaps we'll do a quick review of EM because that's sort of been refactored, and then we'll jump to like what needs to be done in DC. So EM, what I've done, just because this is such a big restructuring, I didn't want to just delete the code or sort of be overwriting stuff as we go, because I wanted to be able to test both versions at once. So the previous code is in old FDEM or old TDEM. And then the newer stuff is in FDEM or TD. So here, if we actually look, I know this is a bit small. I don't know how to make this section bigger. But if we look even just at the file structure of FDEM versus old FDEM, you see now we've got a simulation, which we didn't previously have. We also have broken out the data. So it's very small. There's not much in there, but I think it's a little more transparent having it on its own. And basically the rest is all still there. So if we look then at the base simulation, so it takes a survey in this case, still has a fields method, still has deepred, JVec, all of those good things. So that hasn't, like these are fairly straightforward changes. If we look at the fields, one of the things that changed is now how we access any of the, I guess, properties of the simulation. So this used to, take the survey, and then we would access everything through the survey. Now the fields object is set up and instantiated with a simulation. So if we start to look then at DC, so what I'm going to do, so we've got EM. So let's create a new folder here. And for now, we will just call this new static. And then within that, we'll do, oops, sorry, folder, new DC. Okay, so then if we're looking here at DC, like that. Let's start just by looking at the problem. So I'm going to do two columns here. So we'll have the old problem, and then we're going to create a simulation. DC.py. So in this case, we want to inherit now the base EM simulation. So we'll copy over these from future imports. And then we'll build up everything else as we need it. Oh, strange. Cool. So I'm going to switch back and forth between the EM and the DC because I need to remind myself of what was done. So just let me know if I'm doing something that gets confusing or if you have any questions, please interrupt. So what we want to do is we're going to inherit, I guess, the base EM simulation, and that actually comes with sigma and mu. For DC, mu is not needed, but it still is relevant to EM problems, so it's still going to be attached there. That's something to think about in the future if we actually want to trim that down a little more. So here, we're going to import from, way to go, up, 2, right, 1, 2, base. Base EM simulation. So then when we have our base DC, okay, so then here, sorry, I'm just going to look at, so we do need a survey, and so here we're going to make sure that we import the DC survey. So although this doesn't exist yet, I'm just going to write it, and we'll deal with that shortly. So from .survey DC, we'll import survey. So as I said, that doesn't exist, but it will soon. Or we can actually, let's. So in the survey, here I put the base EM source because it needed access to that. But the survey is actually quite lightweight, so it takes just a source list. And then here for the frequency domain, it had a few handy things like get sources by frequencies and all of that. But we don't actually need that for the DC. The DC is a little more lightweight. Later on, we can implement stuff to get survey lines and things like that. But for now, we will keep it quite trim. So here, what we're going to do, I'm just going to look at some of these imports. So we need the base survey. We probably need these guys. So that might be the right level. Yeah, so don't expect any of this code to work after this discussion, but this will be the general idea. So here we're going to create the just the survey. And so let's actually look and see what's in our current DC survey. So this is what's currently there. So there's a few extra things it looks like that we have here. And that's fine. So these electrode locations, so we'll bring those over. We'll bring over the survey geometry and the survey type. The names of these is something I think we should think about. Because this statement of survey geometry, like to me, I immediately think dipole, dipole, pole, dipole, whatever. Whereas it's really more a statement of actually what's the type of model. Like, is it a half space? Are we doing it from the surface, from a borehole, or something a little more general? But that's okay. We'll leave it as is for now. And then here, Okay, and then one of the important things that we need here is then the source list. So here, we're expecting the source list. So I'm going to pull from EM here in just a sec. Okay, so here, what I did in the EM case is we were expecting, or for the frequency domain EM, we were expecting a list of frequency domain EM sources. So in this case, what we're going to be expecting, something similar, but it'll be DC sources. So here we've got our source list, and then these will be base DC source instances. So this would be a DC source. Okay. Then here in the init, here in the init, one thing that's important that simplifies things quite a bit is now everything is a keyword argument. So in this case, what that means is that the source list needs to be set as a keyword argument. So previously we could have created a survey and just input a list as the first argument, but now you actually need to include the keyword source list. So, and then we just instantiate here on the parent class. So that's what this super does. So super of the survey, it takes self and it will init. And this will set all the keyword arguments. Does that make sense? Cool. The rest of this, it looks like, can basically come over. But I'm not going to do that right now because I think there's pieces of this that need to be thought through a little bit. And I don't actually know if they should be existing on the survey or as utilities for the survey. So that's a question for later. Okay, so now we actually have that survey, so that's going to come in on the base DC simulation. So what else do we need? Okay, we know we've already inherited the rho and sigma, and so you can either invert for rho or sigma with the DC code, and it'll take care of doing the reciprocal if need be. Okay, so that gives us our survey. What else do we need? We need, I'm just going to pull up the frequency domain. Okay, so we'll need the stored J and the J matrix. Those can sit right now just as, well, what actually should happen is, so here, this store J should be a properties. So and then the default will just be false. Here, this J matrix doesn't actually need to be a property because we don't want to serialize it. You only want to serialize the instructions, basically, to recreate the class. So if we were going to try and run a DC forward simulation in parallel, we don't actually want to be serializing and sending around the stored J. We just want to save the instruction that says when you are computing, store the J. So then here, we'll need to init. And then here, this will again just init on the super. So that gives us some pieces of the simulation. Let's take a look and see what else we potentially need. Okay, so we need our fields. So let's deal with that first. So in this case, this can come straight over, right? Nothing has really changed here. We're still going to have the fields pair, get A, all of those kinds of things. So we'll just bring that over. Similarly with get J, JVec, and JTVec, those should basically come straight over, as well as the source term. Okay. Okay, the other thing now that we need, so we have fields, but we also now need deepred. So deepred now lives on the simulation. So I've been putting it right beneath fields because it is the thing that is calculated based on the fields and then doing the sensitivities afterwards, just to try and keep sort of the flow a bit uniform and hopefully logical. So here we've got deepred, takes self, it takes a model. I don't think M can be none. That's interesting. No, it can be. So here, and we can grab this actually. So it used to be in the DC survey. So if we look here at survey DC, you'll see survey.deepred probably. Oh, it's actually inherited from the base. So here, this is actually something interesting, and I didn't appreciate this before, but this could actually sit on the base simulation, right? Because all of these pieces are identical for a frequency domain and for a DC simulation. So instead of necessarily rewriting this here, we can just put this on the base class. Does that make sense?
Where does your base simulation live right now?
So there's the
Okay,
the SimPEG based simulation sits right here. So it's top level file structure. And then each method will have its own base simulation that's got like the few sort of necessary pieces. So here, what we should be able to do is we'll put this on the base EM simulation. Right, so it has, so the base EM simulation's got all the physical property matrices and all of that jazz, and now it can also actually hold deepred. And then since we just inherit this in the whatever simulation and frequency domain in DC, that is then just called and used. So one of the things that's interesting here, sort of as an interim step, is we're actually using this synthetic data class. So we used to actually use the data class to construct this just for ease. I made one small distinction between the synthetic data and the data, and this is something to chat about. But with data, once you've read it in, once you've set your data, I'll let you change it. You can change your uncertainties, and that's fine, but you can't actually change your data. Whereas a synthetic data object, you can. I don't know if that's a distinction worth having. I don't know if you guys have thoughts on that.
I like the distinction that you can have like a deepred and the ops separate.
Yeah.
So I guess that can like avoid a lot of like problem of overwriting.
Yeah.
I'm just thinking of one other thing right now is that if you actually want to create like another data set with another DOps, because you are doing like, I don't know, like Mike, a lot of synthetics and with different models, etc. Is it possible that you have a data object and you do like like a clone with the same surveys, etc. But the ops gonna be like not assigned or different.
Yeah, so that would be totally totally possible. So in that case, you can basically like copy the parameters over.
Yeah.
Or you just instantiate. This would be easier, is if you just instantiate with the same survey, because that's all the data class. So the data class needs. Let's take a look.
Yeah. So basically, you have you still have like a survey object that you can pass along.
Yeah. So each data object has its own survey, because it does need to know about the sources and receivers, so we can index that. And then has deobs, a standard deviation, and a noise floor. So then here, that only distinction. What did you treat? Sorry, as I'm looking at this, I don't actually think we imposed any restriction on, allowing you to change the data or not. Oh, wait. Yes, okay, so that's here. So if the data object, like if deobs has not yet been set, you can go in and set it. But once it's been set, right now we restrict that. So
can you set it as something else? Can you you had two data vectors that you had read in.
Yeah.
Could you set one and be like, oh no, like for some reason that's not the one I wanted associated with this. You set a new one over the top of it, or do you have to like clear the whole data structure object, reinstantiate a new one, and reset it?
So right now you would just need to create a new data, which is 1-in-1. It's data of survey deobs. So
just a thought like this: do we want something like function like get deobs and set deobs? Like you have like the object deobs, but if you really want to change it, like, then you have to actually go through the function set. That's just a thought. Like
yeah, that's not a bad idea. And like two, there's really no reason we actually need to say that you can't overwrite it, like from a code standpoint. I just sort of wonder from like a sanity standpoint, is that useful so that you don't accidentally go in and change your data?
Yeah, no, I like that, but then I know that in some like in some other implementation, like on GIF tool, but even like matplotlib, like when you have objects that are like kind of fixed like that, you can like the way around for that is that you actually have function provided like set deobs that. So it's clear that at this point you want to change the deobs object.
That's fair. So here, adding something like a and maybe like a def clear deobs. Well, I don't think there needs to be a get because because you can still call .deobs and it exists. But yeah, I do think that maybe that's a nice way to work that around.
I feel like we talked about this one other time, but do we have a place that we could potentially store additional information instead of just like the measured potential difference and the uncertainty information? Like say we had inject like current for each injected current value, or potential value that was also measured for each one. And so you're not going to be like using those directly in the inversion, but when it comes to any like the data quality control stuff, you're going to be using those data just like you're using your measured potentials, and you're going to be essentially like querying them in the same way and kind of analyzing them together with those ones to decide how you're setting your uncertainties maybe, or which portions of your data you're keeping or things like that. So at least I've found I've used all of those things kind of in the same context and in the same way. So it was handy to have them in the same place. So it might be, I don't know if it is, but it might be convenient to be able to have that data class be flexible in the sense that you can kind of add specific
I guess
data
there's
columns or whatever.
my thoughts on this. So in a lot of ways, I think we want to keep this SimPEG data structure very light. I think perhaps what you're referring to is much more something like pandas, and actually like using a data frame. And I think that like having utilities for us to interface from a pandas data frame to creating a SimPEG data object, I think like that sort of workflow would be quite powerful. But I think that at least within the scope of what the data class does in the code, we want to keep it lightweight and tailored for that purpose. But I do totally agree that like having something, utilities like to get your data into a pandas type data frame so that you can go in and introspect a lot of those things would be good. But I think that pandas is actually a good solution to that, and I don't think we need to rewrite that.
Yeah, I agree with Lindsay on that point, that a lot of these additional things that are like very like use specific, like for the DC or the EM, and to what type of problem you're probably interested in.
So then somehow we could, because like the data class or the data object is going to have all of these methods associated with it that it can use to then index or somehow manipulate the data in the data object. So is there going to be a way that we can then port all of those utilities over to be able to act on any of the data in this pandas database? Or are we going to have to rewrite all of that functionality?
No, so I think what the way to do that is then you write whatever method it is that's handy. So like if we want to go in and grab dipoles by dipole spacing.
Sure. Yeah.
Write that as a utility that's not attached to a class.
Okay.
And then that's then something that you can attach it to the class, like attach it to the data class in a way that makes sense with working with the data class.
Yeah.
And then you can provide the correct inputs when you're working with a pandas data frame. So you just keep those things separate, and then tie them like where it makes sense. Yeah. Does that make sense?
I think so.
Yeah. One thing I was curious, do we have sort of like an active data kind of thing? So in my case, I might have data at a bunch of time channels, and I'm only interested in inverting a subset. So it seems to sort of fall into the same thing where go store all of your data kind of somewhere else, go and do your analysis and figure out what data you want to invert. And when you have your data vector and you're happy with it, then put it into SimPEG, and then that's sort of what I'm hearing.
So there's two ways you can work through that right now with SimPEG. One thing that you can do, like if you know that you're only going to be working with a subset of the data, then just pull that out and create its own data object. If you potentially want to start an inversion where you're inverting, I'm going to switch to frequency domain or MT just because that's the example in my head. But say you want to start with high frequencies and then add low frequencies as the inversion progresses.
Mm-hmm.
What we can do with that is in the data misfit. I don't actually think this is implemented, but we should.
Yeah, it goes into the directives, right?
No, it actually, well, yeah, so it would go into the directives, and then the data misfit then just has a mapping. So you would just like basically stick a projection matrix outside of the data that all it's doing is selecting which indices of the data you want to work with.
Yeah, I guess my plan was to have some kind of active data, like a Boolean kind of thing, and since the sensitivity matrix was already created, I would just sort of include that in my J and J transpose vector.
Yeah.
Kind of do it in my simulation class, I guess.
I would do it, well, your problem's different because yours depends actually on which data you're using. Like your result, your simulation, you don't have a fields object, right?
No, it's like a linear problem, but I can't use the linear class because it's you can't store that linear operator. So it's a linear problem, but you can't store it because it explodes in size.
Okay.
Could you do it through the WD matrix too, like by setting some of the diagonal element just to 0?
Yeah. That's sort of what I was suggesting with the mapping idea.
So I was just saying that if we don't have like already the projection matrix for the data misfit, that would be like a kind of like a way around by using this matrix that's already there.
Yeah. Do you guys want to keep going on the code, or do you want to switch gears and just chat through pull requests? Like, does this sort of make sense as to where this is going? Maybe what I'll do, I'll give like a quick overview of like maybe next steps. We won't necessarily go through it, and then maybe next time we can go through it in a little more detail. So we've got now like the sketch of our base DC simulation. So then we're going to want to make sure that we can inherit that for the specific simulations, right? So for the cell-centered or for a nodal simulation. So that'll be a next step. Following that, we then also need to go in and update the fields objects. And so one of the things that's worth pointing out is the way I'm instantiating fields objects has changed a little bit. And so what I'm going to do is show you a comparison of the instantiation of the new fields object. So that's going to be on the right-hand side here. And then I'm going to pull up the old one and just, oops. So old one and new one. Okay. So here, let's look at the fields E. Okay. So what we've done is this, so the known fields and the aliased fields used to sit on the outside, right? But those are, what I've done here is I've implemented properties on the base class. And so what we actually want to do is instantiate them in the instantiation. And so why we're doing that is so that they go through, they go through this. And so, because what I've done here is we're going to actually go in and be able to check and make sure that the known fields and the aliased fields, they exist on valid grid locations. So here we can actually go in and provide some sanity checks and basically say, like, hey, the known fields need to exist on either like edges, cell centers, nodes, or whatever. And so we can do all of that sanity checking on the base class and don't actually need to implement it anywhere else. But then that just means that when we set these guys, we actually want to make sure that they go through that properties setter. And so here we do that now in the init. And that's really the biggest change with the fields object. Cool. Yeah, I think that's probably. Deepan or Dom, do you guys have questions or things that you wanted to get out of this that I missed?
I think it's okay.
Okay. Dom, is there anything on?
No, I think it will be great when I start looking at the PFs again. It will be a good way to clean it up. You were I need to get going soon, but you were mentioning about something about drivers at the beginning. What about it?
Yeah, let me bring that up real quick. So this follows a question that John had. And so I think in the IODC right now, there's an inversion method. I don't know actually where it sits. Anyways, he was calling like io.invert or something like that. I don't know if you remember that offhand.
No, I saw that. Yeah, Sug wrote it right to like can all the optimization and everything. I can't remember where it is, but
yeah. So the thing that I think we need to be very careful with when we distribute drivers is like not to obscure the decisions that have been made. Because I think what's happening in John's case is it's just not clear like what beta is being used, what alphas, like all of those kinds of things. And so in a lot of ways, like if there's a useful sort of inversion driver that you've written for yourself to, batch do a whole bunch of synthetic inversions, I would recommend that you put that in like your own research repository and really focus on bringing in utilities that are like general more so into SimPEG. Because I do think that like distributing something that obscures the decisions, it is potentially dangerous. Like it's fine if you write that for yourself because you know what decisions you've made and like where things are baked in. But it is, just something to be cognizant of. And like, I think in a lot of ways, if we can keep things closer, like I think the drivers, Dom, that did for like Craig, were really good in that sense that even if he doesn't understand all of those steps, like setting up the inversion or the regularization or whatever, it's all still clear and very transparent and very close to like the way that we interact with SimPEG.
That's true. That's true. That being said, though, we were talking about it before, right? We should maybe serialize those so that we can easily maintain the drivers. Because the issue with Craig and I is that every time we change the base code, then we need to change all those drivers again. So yeah, it's just hard to maintain the like scripts. You mean? That's what you mean, right?
Yeah, that's totally fair. And so I think that's very fair. And so writing drivers, I think, is fine. It's just we do need to be very, very careful to make sure that all the choices are quite transparent. That's my point.
Yeah, and we can keep them outside of the base code. We could do like a repo of drivers too, I guess.
Yeah, and I think that actually could be a really nice way to go.
I agree.
Cool. Okay, well, we can actually set up a repo for that.
Where do some of these drivers exist now? I didn't know that there were.
Some of them are in like the specific modules. Yeah,
I just haven't come across them.
Yeah. Okay.
They basically sit on people's computers.
Yeah, exactly. Cool. Maybe just quick in other updates, let's maybe take a quick look at pull requests and just see is there anything super urgent. There's two that I would like to bring in fairly soon. So on discretize, there's the 3D sill mesh. And then in SimPEG, this guy follows closely. It includes a whole bunch of upgrades to the time domain code, actually, and a few typo fixes. So if anybody's interested in providing comments on time domain, that would be appreciated. Anybody else have stuff that you want to get in ASAP that's like ready to go, or?
I just have to figure out a way to make the doc strings work, and then I'm good to go.
Cool.
That's pretty much it.
Like the potential for improvement, as we said before, we need to merge local problem, and then this will be good to go because of various apparently merge conflict.
Okay, so this one I think is probably close. I'll take another look at that. And then tebow, there was one on discretize.
Yeah, I might just close it for now.
Okay.
Yeah, it's a fix that I did before before Joe made the VTK improvement, and I just did not notice that it had fixed that. We have slight different implementation, but there is nothing really different. There is still but both of us, Joe and I, we still get a warning that something is depreciated in how we do the VTK stuff. So I was thinking maybe I can use this same branch and pull request to actually fix that warning.
Okay.
But I haven't done it, so right now it's sitting there for nothing. So I was thinking maybe just close it and reopen it when I actually go to fix the warning.
Okay, that sounds good. Cool. Anything else?
Not on my end. I'll see you later, guys.
All right, see you.
Have a good day.
Cool. Yeah, anything else on your end, Deequan?
Not really. Yeah, not really. I'm still kind of catching up. For myself, I think my current focus more in the package of a discretize. I think that's kind of a level I'm kind of more interested in.
Yep.
Yeah, so it's still kind of like working on some of the stuff, like experimenting.
Okay, sounds good.
Yeah. So actually, maybe one comment for the Rowan's comment made in the Slack channel, in like the future of the project.
Oh yeah, sure.
Yeah, he was talking about maybe breaking down to small pieces so people can keep maintaining or kind of that kind of thing. What's your take on that kind of a future, whatever, like?
Sorry, what's my take?
Yeah, or like a general consideration, like.
Yeah, I think that breaking things up makes it much easier to maintain and much easier to invite other people to contribute. So for example, like pieces in the mappings class are like quite transferable to other codes. Like I could see that being useful in PyGimli, for instance. But right now it's not useful to them because it is tied up in SimPEG, so it's just not transparent what's going on there. So I think like having a bit more modularity in that case is better. It does mean that people have to get a little more comfortable with maintaining multiple repositories and like managing branches and things like that. But there's some really good tools out there for helping do that. Okay. So yeah.
Yeah, I think generally I consider it's kind of a good idea. Just kind of instead of having a big item, we can have like a smaller thing, so people can. For example, I'm only using this part of the package. All right, yeah, maybe.
Yeah, agreed. And like I think what would be nice is to sort of go towards the way that Jupyter distributes. Okay. So like, they maintain all of their stuff in a whole bunch of different repositories, but then when you install Jupyter, you get all of it. And so in this case, like we can follow something similar where we break up all of the code, but then if you want everything, then it should be just one install step. So.
All right.
All right. Well, thanks.
Yeah, thank you. Yeah, good stuff. See you guys later. Thanks.
Yeah. You might have one question about